Chapter 14. Deep Computer Vision Using Convolutional Neural Networks. Although IBM's Deep Blue supercomputer beat the chess world champion Garry Kasparov back in 1996, it wasn't until fairly recently that computers were able to reliably perform seemingly trivial tasks such as detecting a puppy in a picture or recognizing spoken words. Why are these tasks so effortless to us humans? The answer lies in the fact that perception largely takes place outside the realm of our consciousness, within specialized visual, auditory, and other sensory modules in our brains. By the time sensory information reaches our consciousness, it is already adorned with high-level features. For example, when you look at a picture of a cute puppy, you cannot choose not to see the puppy, not to notice its cuteness. Nor can you explain how you recognize a cute puppy, it's just obvious to you. Thus, we cannot trust our subjective experience. Perception is not trivial at all, and to understand it we must look at how our sensory modules work. Convolutional neural networks, CNNs, emerged from the study of the brain's visual cortex, and they have been used in computer image recognition since the 1980s. Over the last 10 years, thanks to the increase in computational power, the amount of available training data, and the tricks presented in Chapter 11 for training deep nets, CNNs have managed to achieve superhuman performance on some complex visual tasks. They power image search services, self-driving cars, automatic video classification systems, and more. Moreover, CNNs are not restricted to visual perception. They are also successful at many other tasks, such as voice recognition and natural language processing. However, we will focus on visual applications for now. In this chapter we will explore where CNNs came from, what their building blocks look like, and how to implement them using Keras. Then we will discuss some of the best CNN architectures, as well as other visual tasks, including object detection, classifying multiple objects in an image and placing bounding boxes around them, and semantic segmentation, classifying each pixel according to the class of the object it belongs to. The architecture of the visual cortex. David H. Hubel and Torsten Wiesel performed a series of experiments on cats in 1958-1 and 1959-2, and a few years later on monkeys 3. Giving crucial insights into the structure of the visual cortex. The authors received the Nobel Prize in Physiology or Medicine in 1981 for their work. In particular, they showed that many neurons in the visual cortex have a small local receptive field, meaning they react only to visual stimuli located in a limited region of the visual field. See Figure 14.1, in which the local receptive fields of 5 neurons are represented by dashed circles. The receptive fields of different neurons may overlap, and together they tile the whole visual field. Moreover, the authors showed that some neurons react only to images of horizontal lines, while others react only to lines with different orientations. 2 neurons may have the same receptive field but react to different line orientations. They also noticed that some neurons have larger receptive fields, and they react to more complex patterns that are combinations of the lower-level patterns. These observations led to the idea that the higher-level neurons are based on the outputs of neighboring lower-level neurons. In Figure 14.1, notice that each neuron is connected only to nearby neurons from the previous layer. This powerful architecture is able to detect all sorts of complex patterns in any area of the visual field. These studies of the visual cortex inspired the neocognitron, introduced in 1980, which gradually evolved into what we now call convolutional neural networks. An important milestone was a 1998 paper 5 by Yann LeCun et al. That introduced the famous LeNet 5 architecture, which became widely used by banks to recognize handwritten digits on checks. This architecture has some building blocks that you already know, such as fully connected layers and sigmoid activation functions, but it also introduces 2 new building blocks, convolutional layers and pooling layers. Let's look at them now. Note: why not simply use a deep neural network with fully connected layers for image recognition tasks? Unfortunately, although this works fine for small images, e.g., mist, it breaks down for larger images because of the huge number of parameters it requires. For example, a 100 times 100 pixel image has 10,000 pixels. And if the first layer has just 1,000 neurons, which already severely restricts the amount of information transmitted to the next layer, this means a total of 10 million connections. And that's just the first layer. CNNs solve this problem using partially connected layers and weight sharing. Convolutional layers. The most important building block of a CNN is the convolutional layer. 6 neurons in the first convolutional layer are not connected to every single pixel in the input image, like they were in the layers discussed in previous chapters, but only to pixels in their receptive fields, see figure 14.2. In turn, each neuron in the second convolutional layer is connected only to neurons located within a small rectangle in the first layer. This architecture allows the network to concentrate on small low-level features in the first hidden layer, then assemble them into larger higher-level features in the next hidden layer, and so on. This hierarchical structure is common in real-world images, which is one of the reasons why CNNs work so well for image recognition. Note: all the multilayer neural networks we've looked at so far had layers composed of a long line of neurons, and we had to flatten input images to 1D before feeding them to the neural network. In a CNN, each layer is represented in 2D, which makes it easier to match neurons with their corresponding inputs. A neuron located in row I, column J of a given layer is connected to the outputs of the neurons in the previous layer located in rows I to I plus FH1, columns J to J plus FW1, where FH and FW are the height and width of the receptive field, see figure 14.3. In order for a layer to have the same height and width as the previous layer, it is common to add zeros around the inputs, as shown in the diagram. This is called zero padding. It is also possible to connect a large input layer to a much smaller layer by spacing out the receptive fields, as shown in figure 14.4. This dramatically reduces the model's computational complexity. The horizontal or vertical step size from one receptive field to the next is called the stride. In the diagram, a 5x7 input layer, plus zero padding, is connected to a 3x4 layer, using 3x3 receptive fields and a stride of 2. In this example, the stride is the same in both directions, but it does not have to be so. A neuron located in row I, column J in the upper layer is connected to the outputs of the neurons in the previous layer located in rows I times SH to I times SH plus FH1, columns J times SW to J times SW plus FW1, where SH and SW are the vertical and horizontal strides. Filters. A neuron's weights can be represented as a small image the size of the receptive field. For example, figure 14.5 shows two possible sets of weights, called filters, or convolution kernels, or just kernels. The first one is represented as a black square with a vertical white line in the middle. It's a 7x7 matrix full of zeros except for the central column, which is full of ones. Neurons using these weights will ignore everything in their receptive field except for the central vertical line, since all inputs will be multiplied by 0, except for the ones in the central vertical line. The second filter is a black square with a horizontal white line in the middle. Neurons using these weights will ignore everything in their receptive field except for the central horizontal line. Now if all neurons in a layer use the same vertical line filter, and the same bias term, and you feed the network the input image shown in figure 14.5, the bottom image, the layer will output the top left image. Notice that the vertical white lines get enhanced while the rest gets blurred. Similarly, the upper right image is what you get if all neurons use the same horizontal line filter. Notice that the horizontal white lines get enhanced while the rest is blurred out. Thus, a layer full of neurons using the same filter outputs a feature map, which highlights the areas in an image that activate the filter the most. But don't worry, you won't have to define the filters manually. Instead, during training, the convolutional layer will automatically learn the most useful filters for its task, and the layers above will learn to combine them into more complex patterns. In this equation, Z, J, K is the output of the neuron located in row I, column J in feature map K of the convolutional layer, layer L. As explained earlier, SHR and SW are the vertical and horizontal strides, FH and FW are the height and width of the receptive field, and FN is the number of feature maps in the previous layer, layer L1. 11-foot, J, K is the output of the neuron located in layer L1, row I, column J, feature map K, or channel K, if the previous layer is the input layer. BK is the bias term for feature map K in layer L. You can think of it as a knob that tweaks the overall brightness of the feature map K, Wu, V, K. K is the connection weight between any neuron in feature map K of the layer L and its input located at row U, column V, relative to the neuron's receptive field, and feature map K. Yikes, it's a 4D tensor, we haven't seen this before. What do all these dimensions mean? Well, there are two sample images, which explains the first dimension. Then each image is 70 × 120, since that's the size we specified when creating the center crop layer. The original images were for 27 by 640. This explains the second and third dimensions. And lastly, each pixel holds one value per color channel, and there are 3 of them, red, green, and blue, which explains the last dimension. Now let's create a 2D convolutional layer and feed it these images to see what comes out. For this, Keras provides a convolution 2D layer, alias conv2D. Under the hood, this layer relies on TensorFlow's tf.nn.conv2D operation. Let's create a convolutional layer with 32 filters, each of size 7 by 7, using kernel_size equals 7, which is equivalent to using kernel_size sat_smiley 7, and apply this layer to our small batch of 2 images. Note: when we talk about a 2D convolutional layer, 2D refers to the number of spatial dimensions, height and width, but as you can see, the layer takes for D inputs. As we saw, the 2 additional dimensions are the batch size, first dimension, and the channels, last dimension. The output shape is similar to the input shape, with 2 main differences. First, there are 32 channels instead of 3. This is because we set filters equals 32, so we get 32 output feature maps, instead of the intensity of red, green, and blue at each location. We now have the intensity of each feature at each location. Second, the height and width have both shrunk by 6 pixels. This is due to the fact that the conv2D layer does not use any zero padding by default, which means that we lose a few pixels on the sides of the output feature maps, depending on the size of the filters. In this case, since the kernel size is 7, we lose 6 pixels horizontally and 6 pixels vertically, i.e., 3 pixels on each side. Warning: the default option is surprisingly named padding equals valid, which actually means no zero padding at all. This name comes from the fact that in this case every neuron's receptive field lies strictly within valid positions inside the input. It does not go out of bounds. It's not a Keras naming quirk, everyone uses this odd nomenclature. If instead we set padding equals same, then the inputs are padded with enough zeros on all sides to ensure that the output feature maps end up with the same size as the inputs, hence the name of this option. These 2 padding options are illustrated in figure 14.7. For simplicity, only the horizontal dimension is shown here, but of course the same logic applies to the vertical dimension as well. If the stride is greater than 1 in any direction, then the output size will not be equal to the input size, even if padding equals same. For example, if you set strides equals 2, or equivalently strides sat_smiley 2, then the output feature maps will be 35 by 60, halved both vertically and horizontally. Figure 14.8 shows what happens when strides equals 2, with both padding options. If you are curious, this is how the output size is computed. With padding equals valid, if the width of the input is E, then the output width is equal to EFH plus SHR, rounded down. Recall that FH is the kernel width, and SHR is the horizontal stride. Any remainder in the division corresponds to ignored columns on the right side of the input image. The same logic can be used to compute the output height and any ignored rows at the bottom of the image. With padding equals same, the output width is equal to each, rounded up. To make this possible, the appropriate number of 0 columns are padded to the left and right of the input image, an equal number if possible, or just one more on the right side. Assuming the output width is AU, then the number of padded 0 columns is AU1 times SH plus FHE. Again, the same logic can be used to compute the output height and the number of padded rows. Now let's look at the layers weights, which were noted WU, V, K, K and BK in equation 14:1. Just like a dense layer, a conv2D layer holds all the layers weights, including the kernels and biases. The kernels are initialized randomly, while the biases are initialized to 0. These weights are accessible as TF variables via the weights attribute, or as numpy arrays via the get_weights method. The kernel's array is 4D, and its shape is a kernel_height, kernel_width, input_channels, output_channels. The biases array is 1D, with shape output_channels. The number of output channels is equal to the number of output feature maps, which is also equal to the number of filters. Most importantly, note that the height and width of the input images do not appear in the kernel's shape. This is because all the neurons in the output feature maps share the same weights, as explained earlier. This means that you can feed images of any size to this layer, as long as they are at least as large as the kernels, and if they have the right number of channels, 3 in this case. Lastly, you will generally want to specify an activation function, such as ReLU, when creating a conv2D layer, and also specify the corresponding kernel initializer, such as HE initialization. This is for the same reason as for dense layers. A convolutional layer performs a linear operation, so if you stacked multiple convolutional layers without any activation functions, they would all be equivalent to a single convolutional layer, and they wouldn't be able to learn anything really complex. As you can see, convolutional layers have quite a few hyperparameters: filters, kernel_size, padding, strides, activation, kernel_initializer, etc. As always, you can use cross-validation to find the right hyperparameter values, but this is very time-consuming. We will discuss common CNN architectures later in this chapter, to give you some idea of which hyperparameter values work best in practice. Memory requirements. Another challenge with CNNs is that the convolutional layers require a huge amount of RAM. This is especially true during training, because the reverse pass of backpropagation requires all the intermediate values computed during the forward pass. For example, consider a convolutional layer with 205 by 5 filters, with stride 1 and same padding. If the input is a 150 by 100 RGB image, 3 channels, then the number of parameters is 5 by 5 by 3 plus 1 times 200 is equal to 15,200. The plus 1 corresponds to the bias terms, which is fairly small compared to a fully connected layer. 7 However, each of the 200 feature maps contains 150 by 100 neurons. And each of these neurons needs to compute a weighted sum of its 5 times 5 times 3 is equal to 75 inputs. That's a total of 225 million float multiplications. Not as bad as a fully connected layer, but still quite computationally intensive. Moreover, if the feature maps are represented using 32-bit floats, then the convolutional layer's output will occupy 200 times 150 times 100 times 32 is equal to 96 million bits, 12 megabytes of RAM. 8 And that's just for one instance. If a training batch contains 100 instances, then this layer will use up 1.2 gigabytes of RAM. During inference, i.e., when making a prediction for a new instance, the RAM occupied by one layer can be released as soon as the next layer has been computed, so you only need as much RAM as required by 2 consecutive layers. But during training, everything computed during the forward pass needs to be preserved for the reverse pass, so the amount of RAM needed is, at least, the total amount of RAM required by all layers. Tip: if training crashes because of an out-of-memory error, you can try reducing the mini-batch size. Alternatively, you can try reducing dimensionality using a stride, removing a few layers, using 16-bit floats instead of 32-bit floats, or distributing the CNN across multiple devices. You will see how to do this in Chapter 19. Now let's look at the second common building block of CNNs, the pooling layer. Pooling layers. Once you understand how convolutional layers work, the pooling layers are quite easy to grasp. Their goal is to subsample, i.e., shrink the input image in order to reduce the computational load, the memory usage, and the number of parameters, thereby limiting the risk of overfitting. Just like in convolutional layers, each neuron in a pooling layer is connected to the outputs of a limited number of neurons in the previous layer, located within a small rectangular receptive field. You must define its size, the stride, and the padding type, just like before. However, a pooling neuron has no weights. All it does is aggregate the inputs using an aggregation function such as the max or mean. Figure 14.9 shows a max pooling layer, which is the most common type of pooling layer. In this example, we use a 2x2 pooling kernel, 9 with a stride of 2 and no padding. Only the max input value in each receptive field makes it to the next layer, while the other inputs are dropped. For example, in the lower left receptive field in Figure 14.9, the input values are 1, 5, 3, 2, so only the max value, 5, is propagated to the next layer. Because of the stride of 2, the output image has half the height and half the width of the input image, rounded down since we use no padding. Implementing pooling layers with Keras. The following code creates a max pooling 2D layer, alias maxpool 2D, using a 2x2 kernel. The strides default to the kernel size, so this layer uses a stride of 2, horizontally and vertically. By default, it uses valid padding, i.e., no padding at all. To create an average pooling layer, just use average pooling 2D, alias average pool 2D, instead of maxpool 2D. As you might expect, it works exactly like a max pooling layer, except it computes the mean rather than the maximum. Average pooling layers used to be very popular, but people mostly use max pooling layers now, as they generally perform better. This may seem surprising, since computing the mean generally loses less information than computing the maximum. But on the other hand, max pooling preserves only the strongest features, getting rid of all the meaningless ones, so the next layers get a cleaner signal to work with. Moreover, max pooling offers stronger translation invariance than average pooling, and it requires slightly less compute. Note that max pooling and average pooling can be performed along the depth dimension instead of the spatial dimensions, although it's not as common. This can allow the CNN to learn to be invariant to various features. For example, it could learn multiple filters, each detecting a different rotation of the same pattern, such as handwritten digits, see Figure 14.11, and the depth-wise max pooling layer would ensure that the output is the same regardless of the rotation. The CNN could similarly learn to be invariant to anything, thickness, brightness, skew, color, and so on. This layer reshapes its inputs to split the channels into groups of the desired size, pool_size, then it uses tf.reduce_max to compute the max of each group. This implementation assumes that the stride is equal to the pool size, which is generally what you want. Alternatively, you could use TensorFlow's tf.nn.max_pool operation and wrap in a lambda layer to use it inside a Keras model, but sadly this op does not implement depth-wise pooling for the GPU, only for the CPU. One last type of pooling layer that you will often see in modern architectures is the global average pooling layer. It works very differently. All it does is compute the mean of each entire feature map. It's like an average pooling layer using a pooling kernel with the same spatial dimensions as the inputs. This means that it just outputs a single number per feature map and per instance. Although this is of course extremely destructive, most of the information in the feature map is lost. It can be useful just before the output layer, as you will see later in this chapter. To create such a layer, simply use the Global Average Pooling 2D class, alias Global Average Pool 2D. CNN architectures. Typical CNN architectures stack a few convolutional layers, each one generally followed by a ReLU layer, then a pooling layer, then another few convolutional layers, plus ReLU, then another pooling layer, and so on. The image gets smaller and smaller as it progresses through the network, but it also typically gets deeper and deeper, i.e., with more feature maps, thanks to the convolutional layers, see Figure 1412. At the top of the stack, a regular feed-forward neural network is added, composed of a few fully connected layers, plus ReLUs, and the final layer outputs the prediction, e.g., a softmax layer that outputs estimated class probabilities. Tip: a common mistake is to use convolution kernels that are too large. For example, instead of using a convolutional layer with a 5x5 kernel, stack 2 layers with 3x3 kernels. It will use fewer parameters and require fewer computations, and it will usually perform better. One exception is for the first convolutional layer. It can typically have a large kernel, e.g., 5x5, usually with a stride of 2 or more. This will reduce the spatial dimension of the image without losing too much information, and since the input image only has 3 channels in general, it will not be too costly. Let's go through this code. We use the functools.partial function, introduced in Chapter 11, to define default conv2d, which acts just like conv2d but with different default arguments, a small kernel size of 3, same padding, the ReLU activation function, and its corresponding he initializer. Next, we create the sequential model. Its first layer is a default conv2d with 64 fairly large filters, 7x7. It uses the default stride of 1 because the input images are not very large. It also sets input_shape SatSmiley 28, 28, 1, because the images are 28 by 28 pixels, with a single color channel, i.e., grayscale. When you load the fashion NIST dataset, make sure each image has this shape. You may need to use np.reshape or np.expandums to add the channel's dimension. Alternatively, you could use a reshape layer as the first layer in the model. We then add a max pooling layer that uses the default pool size of 2, so it divides each spatial dimension by a factor of 2. Then we repeat the same structure twice, 2 convolutional layers followed by a max pooling layer. For larger images, we could repeat this structure several more times. The number of repetitions is a hyperparameter you can tune. Note that the number of filters doubles as we climb up the CNN toward the output layer. It is initially 64, then 128, then 256. It makes sense for it to grow, since the number of low-level features is often fairly low, e.g., small circles, horizontal lines, but there are many different ways to combine them into high-level features. It is a common practice to double the number of filters after each pooling layer, since a pooling layer divides each spatial dimension by a factor of 2. We can afford to double the number of feature maps in the next layer without fear of exploding the number of parameters, memory usage, or computational load. Next is the fully connected network, composed of 2 hidden dense layers and a dense output layer. Since it's a classification task with 10 classes, the output layer has 10 units, and it uses the softmax activation function. Note that we must flatten the inputs just before the first dense layer, since it expects a 1D array of features for each instance. We also add 2 dropout layers, with a dropout rate of 50% each, to reduce overfitting. If you compile this model using the sparse_categorical_cross-entropy loss and you fit the model to the fashion NIST training set, it should reach over 92% accuracy on the test set. It's not state-of-the-art, but it is pretty good, and clearly much better than what we achieved with dense networks in Chapter 10. Over the years, variants of this fundamental architecture have been developed, leading to amazing advances in the field. A good measure of this progress is the error rate in competitions such as the ILS-VRC ImageNet Challenge. In this competition, the top 5 error rate for image classification, that is, the number of test images for which the system's top 5 predictions did not include the correct answer, fell from over 26% to less than 2.3% in just 6 years. The images are fairly large, e.g., 256 pixels high, and there are 1,000 classes, some of which are really subtle. Try distinguishing 120 dog breeds. Looking at the evolution of the winning entries is a good way to understand how CNNs work and how research in deep learning progresses. We will first look at the classical LeNet 5 architecture, 1998, then several winners of the ILS-VRC Challenge, AlexNet, 2012, GoogleNet, 2014, ResNet, 2015, and SENet, 2017. Along the way, we will also look at a few more architectures, including Exception, ResNext, DenseNet, MobileNet, CSPNet, and EfficientNet. LeNet 5. The LeNet 5 architecture 10 is perhaps the most widely known CNN architecture. As mentioned earlier, it was created by Yann LeCun in 1998 and has been widely used for handwritten digit recognition (NIST). It is composed of the layers shown in Table 14.1. As you can see, this looks pretty similar to our fashion NIST model, a stack of convolutional layers and pooling layers, followed by a dense network. Perhaps the main difference with more modern classification CNNs is the activation functions. Today, we would use ReLU instead of TAN and softmax instead of RBF. There were several other minor differences that don't really matter much, but in case you are interested, they are listed in this chapter's notebook at https://hamel.info/colab3. Yann LeCun's website also features great demos of LeNet 5 classifying digits. AlexNet. The AlexNet CNN Architecture 11 won the 2012 ILS-VRC Challenge by a large margin. It achieved a top 5 error rate of 17%, while the second best competitor achieved only 26%. AlexNet was developed by Alex Krzyzewski, hence the name, Ilya Sutskever, and Jeffrey Hinton. It is similar to LeNet 5, only much larger and deeper, and it was the first to stack convolutional layers directly on top of one another, instead of stacking a pooling layer on top of each convolutional layer. Table 14.2 presents this architecture. To reduce overfitting, the authors used 2 regularization techniques. First, they applied dropout, introduced in Chapter 11, with a 50% dropout rate during training to the outputs of layers F9 and F10. Second, they performed data augmentation by randomly shifting the training images by various offsets, flipping them horizontally, and changing the lighting conditions. Data augmentation. Data augmentation artificially increases the size of the training set by generating many realistic variants of each training instance. This reduces overfitting, making this a regularization technique. The generated instances should be as realistic as possible. Ideally, given an image from the augmented training set, a human should not be able to tell whether it was augmented or not. Simply adding white noise will not help. The modifications should be learnable. White noise is not. For example, you can slightly shift, rotate, and resize every picture in the training set by various amounts and add the resulting pictures to the training set. See Figure 14.13. To do this, you can use Keras's data augmentation layers, introduced in Chapter 13, e.g., random crop, random rotation, etc. This forces the model to be more tolerant to variations in the position, orientation, and size of the objects in the pictures. To produce a model that's more tolerant of different lighting conditions, you can similarly generate many images with various contrasts. In general, you can also flip the pictures horizontally, except for text and other asymmetrical objects. By combining these transformations, you can greatly increase your training set size. Data augmentation is also useful when you have an unbalanced dataset. You can use it to generate more samples of the less frequent classes. This is called the synthetic minority oversampling technique, or SMOT for short. AlexNet also uses a competitive normalization step immediately after the ReLU step of layers C1 and C3, called local response normalization, LRN. The most strongly activated neurons inhibit other neurons located at the same position in neighboring feature maps. Such competitive activation has been observed in biological neurons. This encourages different feature maps to specialize, pushing them apart and forcing them to explore a wider range of features, ultimately improving generalization. Equation 14-2 shows how to apply LRN. In this equation, BI is the normalized output of the neuron located in feature map I, at some row U and column V. Note that in this equation we consider only neurons located at this row and column, so U and V are not shown. RE is the activation of that neuron after the ReLU step, but before normalization. K, alpha, beta, and R are hyperparameters. K is called the bias, and R is called the depth radius. Fn is the number of feature maps. For example, if R equals 2 and a neuron has a strong activation, it will inhibit the activation of the neurons located in the feature maps immediately above and below its own. In AlexNet, the hyperparameters are set as R equals 5, alpha equals 0.0001, beta equals 0.75, and K equals 2. You can implement this step by using the tf.nn.local_response_normalization function, which you can wrap in a lambda layer if you want to use it in a Keras model. A variant of AlexNet called ZFNet12 was developed by Matthew Zeiler and Rob Fergus and won the 2013 ILS-VRC challenge. It is essentially AlexNet with a few tweaked hyperparameters, number of feature maps, kernel size, stride, etc. GoogleNet. The GoogleNet architecture was developed by Christian Szegedy et al. From Google Research, 13, and it won the ILS-VRC 2014 challenge by pushing the top 5 error rate below 7%. This great performance came in large part from the fact that the network was much deeper than previous CNNs, as you'll see in Figure 14-15. This was made possible by subnetworks called inception modules, 14, which allow GoogleNet to use parameters much more efficiently than previous architectures. GoogleNet actually has 10 times fewer parameters than AlexNet, roughly 6 million instead of 60 million. Figure 14-14 shows the architecture of an inception module. The notation 3x3 plus 1s means that the layer uses a 3x3 kernel, stride 1, and same padding. The input signal is first fed to 4 different layers in parallel. All convolutional layers use the ReLU activation function. Note that the top convolutional layers use different kernel sizes, 1x1, 3x3, and 5x5, allowing them to capture patterns at different scales. Also note that every single layer uses a stride of 1 and the same padding, even the max pooling layer, so their outputs all have the same height and width as their inputs. This makes it possible to concatenate all the outputs along the depth dimension in the final depth concatenation layer, i.e., to stack the feature maps from all 4 top convolutional layers. It can be implemented using Keras's concatenate layer, using the default axis equals 1. You only look once. YOLO is a fast and accurate object detection architecture proposed by Joseph Redman et al. In a 2015 paper. 33. It is so fast that it can run in real time on a video, as seen in Redman's demo. YOLO's architecture is quite similar to the one we just discussed, but with a few important differences. For each grid cell, YOLO only considers objects whose bounding box center lies within that cell. The bounding box coordinates are relative to that cell, where 0, 0 means the top left corner of the cell and 1, 1 means the bottom right. However, the bounding box's height and width may extend well beyond the cell. It outputs 2 bounding boxes for each grid cell, instead of just 1, which allows the model to handle cases where 2 objects are so close to each other that their bounding box centers lie within the same cell. Each bounding box also comes with its own objectness score. YOLO also outputs a class probability distribution for each grid cell, predicting 20 class probabilities per grid cell since YOLO was trained on the Pascal VOC dataset, which contains 20 classes. This produces a coarse class probability map. Note that the model predicts one class probability distribution per grid cell, not per bounding box. However, it's possible to estimate class probabilities for each bounding box during post-processing by measuring how well each bounding box matches each class in the class probability map. For example, imagine a picture of a person standing in front of a car. There will be two bounding boxes, one large horizontal one for the car, and a smaller vertical one for the person. These bounding boxes may have their centers within the same grid cell. So how can we tell which class should be assigned to each bounding box? Well, the class probability map will contain a large region where their car class is dominant, and inside it there will be a smaller region where their person class is dominant. Hopefully, the car's bounding box will roughly match their car region, while the person's bounding box will roughly match their person region. This will allow the correct class to be assigned to each bounding box. YOLO was originally developed using Darknet, an open-source deep learning framework initially developed in C by Joseph Redman, but it was soon ported to TensorFlow, Keras, PyTorch, and more. It was continuously improved over the years, with YOLF2, YOLF3, and YOLO 9000, again by Joseph Redman et al., YOLF4 by Alexei Bochkovsky et al., YOLF5 by Glenn Jucker, and PPYOLO by Xianglong et al. Each version brought some impressive improvements in speed and accuracy, using a variety of techniques. For example, YOLF3 boosted accuracy in part thanks to anchor priors, exploiting the fact that some bounding box shapes are more likely than others, depending on the class, e.g., people tend to have vertical bounding boxes, while cars usually don't. They also increased the number of bounding boxes per grid cell. They trained on different datasets with many more classes, up to 9,000 classes organized in a hierarchy. In the case of YOLO 9000, they added skip connections to recover some of the spatial resolution that is lost in the CNN. We will discuss this shortly, when we look at semantic segmentation, and much more. There are many variants of these models too, such as YOLF4 Tiny, which is optimized to be trained on less powerful machines and which can run extremely fast, at over 1000 frames per second, but with a slightly lower mean average precision map. Mean average precision. A very common metric used in object detection tasks is the mean average precision. Mean average sounds a bit redundant, doesn't it? To understand this metric, let's go back to two classification metrics we discussed in Chapter 3, Precision and Recall. Remember the trade-off: the higher the recall, the lower the precision. You can visualize this in a precision recall curve, see Figure 3.6. To summarize this curve into a single number, we could compute its area under the curve, AUC. But note that the precision recall curve may contain a few sections where precision actually goes up when recall increases, especially at low recall values. You can see this at the top left of Figure 3.6. This is one of the motivations for the map metric. Suppose the classifier has 90% precision at 10% recall, but 96% precision at 20% recall. There's really no trade-off here. It simply makes more sense to use the classifier at 20% recall rather than at 10% recall, as you will get both higher recall and higher precision. So instead of looking at the precision at 10% recall, we should really be looking at the maximum precision that the classifier can offer with at least 10% recall. It would be 96%, not 90%. Therefore, one way to get a fair idea of the model's performance is to compute the maximum precision you can get with at least 0% recall, then 10% recall, 20%, and so on up to 100%, and then calculate the mean of these maximum precisions. This is called the average precision, AP, metric. Now when there are more than two classes, we can compute the AP for each class, and then compute the mean AP map. That's it. In an object detection system, there is an additional level of complexity. what if the system detected the correct class, but at the wrong location, i.e., the bounding box is completely off? Surely we should not count this as a positive prediction. One approach is to define an IOU threshold. For example, we may consider that a prediction is correct only if the IOU is greater than, say, 0.5, and the predicted class is correct. The corresponding map is generally noted map at 0.5, or map at 50%, or sometimes just AP50. In some competitions, such as the Pascal VOC Challenge, this is what is done. In others, such as the COCO competition, the map is computed for different IOU thresholds, 0.50, 0.55, 0.60, 0.95, and the final metric is the mean of all these maps, noted map at 0.50, 0.95, or map at 0.50: 0.05, 0.95. Yes, that's a mean average. Many object detection models are available on TensorFlow Hub, often with pre-trained weights, such as YOL5, 34 SSD, 35 faster RCNN, 36 and efficient DET. 37 SSD and efficient DET are look-once detection models, similar to YOLO. Efficient DET is based on the efficient net convolutional architecture. Faster RCNN is more complex. The image first goes through a CNN. Then the output is passed to a region proposal network, RPN, that proposes bounding boxes that are most likely to contain an object. A classifier is then run for each bounding box, based on the cropped output of the CNN. The best place to start using these models is TensorFlow Hub's excellent object detection tutorial. So far, we've only considered detecting objects in single images. But what about videos? Objects must not only be detected in each frame, they must also be tracked over time. Let's take a quick look at object tracking now. Object tracking. Object tracking is a challenging task. Objects move, they may grow or shrink as they get closer to or further away from the camera. Their appearance may change as they turn around or move to different lighting conditions or backgrounds. They may be temporarily occluded by other objects, and so on. One of the most popular object tracking systems is DeepSORT. 38. It is based on a combination of classical algorithms and deep learning. It uses Kalman filters to estimate the most likely current position of an object given prior detections, and assuming that objects tend to move at a constant speed. It uses a deep learning model to measure the resemblance between new detections and existing tracked objects. Lastly, it uses the Hungarian algorithm to map new detections to existing tracked objects, or to new tracked objects. This algorithm efficiently finds the combination of mappings that minimizes the distance between the detections and the predicted positions of tracked objects, while also minimizing the appearance discrepancy. For example, imagine a red ball that just bounced off a blue ball traveling in the opposite direction. Based on the previous positions of the balls, the Kalman filter will predict that the balls will go through each other. Indeed, it assumes that objects move at a constant speed, so it will not expect the bounce. If the Hungarian algorithm only considered positions, then it would happily map the new detections to the wrong balls, as if they had just gone through each other and swapped colors. But thanks to the resemblance measure, the Hungarian algorithm will notice the problem. Assuming the balls are not too similar, the algorithm will map the new detections to the correct balls. Tip: there are a few DeepSORT implementations available on GitHub, including a TensorFlow implementation of YOLF4 plus DeepSORT, https://github.com/theiguyscode/YOLOv4-DeepSORT. So far we have located objects using bounding boxes. This is often sufficient, but sometimes you need to locate objects with much more precision, for example, to remove the background behind a person during a video conference call. Let's see how to go down to the pixel level. Semantic segmentation. In semantic segmentation, each pixel is classified according to the class of the object it belongs to, e.g., road, car, pedestrian, building, etc., as shown in Figure 1427. Note that different objects of the same class are not distinguished. For example, all the bicycles on the right side of the segmented image end up as one big lump of pixels. The main difficulty in this task is that when images go through a regular CNN, they gradually lose their spatial resolution due to the layers with strides greater than 1, so a regular CNN may end up knowing that there's a person somewhere in the bottom left of the image, but it will not be much more precise than that. Just like for object detection, there are many different approaches to tackle this problem, some quite complex. However, a fairly simple solution was proposed in the 2015 paper by Jonathan Long et al. I mentioned earlier, on fully convolutional networks. The authors start by taking a pre-trained CNN and turning it into an FCN. The CNN applies an overall stride of 32 to the input image, i.e., if you add up all the strides greater than 1, meaning the last layer outputs feature maps that are 32 times smaller than the input image. This is clearly too coarse, so they added a single upsampling layer that multiplies the resolution by 32. There are several solutions available for upsampling, increasing the size of an image, such as bilinear interpolation, but that only works reasonably well up to ×4 or ×8. Instead, they use a transposed convolutional layer, 39. This is equivalent to first stretching the image by inserting empty rows and columns, full of zeros, then performing a regular convolution, see Figure 1428. Alternatively, some people prefer to think of it as a regular convolutional layer that uses fractional strides, e.g., the stride is 1/2 in Figure 1428. The transposed convolutional layer can be initialized to perform something close to linear interpolation, but since it is a trainable layer, it will learn to do better during training. In Keras, you can use the conv2D transpose layer. Note: in a transposed convolutional layer, the stride defines how much the input will be stretched, not the size of the filter steps, so the larger the stride, the larger the output, unlike for convolutional layers or pooling layers. Other Keras convolutional layers. Keras also offers a few other kinds of convolutional layers. tf.keras.layers, conv1d. A convolutional layer for 1D inputs, such as time series or text, sequences of letters or words, as you will see in Chapter 15. tf.keras.layers, conv3d. A convolutional layer for 3D inputs, such as 3D PET scans. Dilation_8. Setting the dilation_8 hyperparameter of any convolutional layer to a value of 2 or more creates an atraus convolutional layer. Atraus is French for with holes. This is equivalent to using a regular convolutional layer with a filter dilated by inserting rows and columns of zeros, i.e., holes. For example, a 1/3 filter equal to may be dilated with a dilation rate of 4, resulting in a dilated filter of. This lets the convolutional layer have a larger receptive field at no computational price and using no extra parameters. Using transposed convolutional layers for upsampling is okay, but still too imprecise. To do better, Long et al. Added skip connections from lower layers. For example, they upsampled the output image by a factor of 2 instead of 32, and they added the output of a lower layer that had this double resolution. Then they upsampled the result by a factor of 16, leading to a total upsampling factor of 32, see Figure 1429. This recovered some of the spatial resolution that was lost in earlier pooling layers. In their best architecture, they used a second similar skip connection to recover even finer details from an even lower layer. In short, the output of the original CNN goes through the following extra steps: upsample ×2, at the output of a lower layer, of the appropriate scale, upsample ×2, at the output of an even lower layer, and finally upsample ×8. It is even possible to scale up beyond the size of the original image. This can be used to increase the resolution of an image, which is a technique called superresolution. Instance segmentation is similar to semantic segmentation, but instead of merging all objects of the same class into one big lump, each object is distinguished from the others, e.g., it identifies each individual bicycle. For example, the mask RCNN architecture, proposed in a 2017 paper 40 by Kaminghe et al., extends the faster RCNN model by additionally producing a pixel mask for each bounding box. So, not only do you get a bounding box around each object, with a set of estimated class probabilities, but you also get a pixel mask that locates pixels in the bounding box that belong to the object. This model is available on TensorFlow Hub, pre-trained on the COCO 2017 dataset. The field is moving fast, though, so if you want to try the latest and greatest models, please check out the state-of-the-art section of https://paperswithcode.com. As you can see, the field of deep computer vision is vast and fast-paced, with all sorts of architectures popping up every year. Almost all of them are based on convolutional neural networks. But since 2020 another neural net architecture has entered the computer vision space, transformers, which we will discuss in Chapter 16. The progress made over the last decade has been astounding, and researchers are now focusing on harder and harder problems, such as adversarial learning, which attempts to make the network more resistant to images designed to fool it, explainability, understanding why the network makes a specific classification, realistic image generation, which we will come back to in Chapter 17. Single-shot learning, a system that can recognize an object after it has seen it just once, predicting the next frames in a video, combining text and image tasks, and more. Now on to the next chapter, where we will look at how to process sequential data such as time series using recurrent neural networks and convolutional neural networks.